Hi folks, and welcome to Open Analysis Live. We are back finally after a 2-month hiatus, and what we're bringing to you today is something that you guys have asked for many times, and it's something that me and Sean have worked on for the past couple weeks now, trying to put this together. This is a deep dive multi-part tutorial series, so there's going to be multiple videos, and what we're going to do is we're going to take you from the very beginning of reverse engineering a piece of malware to the end where we reverse engineer the C2 protocol and we end up sinkholing the botnet. So we're going to go the whole way through. I think it's very interesting. There's a cool story behind it, and there's a whole bunch of different tips and tricks that we're going to show you along the way. There's some IDA scripting, there's some debugging, lots of reverse engineering in IDA, lots of sort of context behind some of the videos that we've been showing you in the past. So this hopefully sort of puts all those concepts together into one series. And it's something that, again, we've been working on for a while, and finally I think we have it in a format that is going to be good to consume for you guys. So hopefully it works, and hopefully you guys enjoy this. And if you do, we'll try and produce more of these sort of longer, in-depth tutorial series. So before we get started, a little bit of housekeeping. The reason why we haven't put out a lot of videos, other than obviously this, coronavirus stuff. Coronavirus! Is we've been working on UnPACME in most of our free time, which is our free automated malware unpacking service.
UnPACME, a malware unpacking service from Open Analysis. Expose the malware before it exposes you.
If you haven't checked it out and you want to unpack some malware, head on over there. It's free, and hopefully it's a useful service for you guys. We're adding new features every day and making it faster. Okay, so before we dive into this, I have to give you a little bit of history here. This piece of malware has been around for 10 years. It is like a zombie that just will not die. And what sort of made me think about going into this and revisiting it is recently Carson had this awesome tutorial on his channel about worms and self-propagating malware, which I'll link in the description below if you guys haven't checked it out. The cool thing about worms is that they kind of never go away. As long as there's still vulnerable systems out there that they can spread to, they continue to live on long after the developers and the operators have moved on to other things. So these are kind of like a blast from the past, but what's cool about it is a lot of the time they are still active. And this particular one is still active. So I first ran across this around 7 years ago or so on the job. And for a while it was under NDA, but that's long past, so I can talk about this a little bit. I'll be abstract just so that I don't expose anything. But basically, I ran into this thing way back in the day, 7 years ago. And at the time, I wasn't doing a lot of deep dive reverse engineering. I was doing incident response. So for me, the main things I was trying to figure out were how is it propagating? How can I detect it? And how do I stop it? So I wasn't really looking at how it worked internally or what the purpose of it was. I was just kind of looking at like how can I identify it and how can I stop it. So what I can tell you before we dive in here is that it copies itself to USB drives, and it starts an auto-run file, creates an auto-run file which will automatically launch when somebody browses to that folder in the USB key. Now this is an old vulnerability that has long since been mitigated by Windows, but older systems, if they don't have those patches, this will still spread. So that was the persistence mechanism, and what it actually did was it would call out to CNC and receive some instructions. And I won't spoil what those instructions are here today. We're going to go in and reverse engineer it and figure out what they are. But what I could tell just by looking at the behavior back when I was an incident responder, not doing any deep dive reverse engineering, was that it was using the IRC protocol. So for those of you who are Zoomers, IRC is a protocol that used to be used for chatting. It's a text-based protocol. I fucking hope it's a text-based protocol. Anyway, it's really easy to identify on the network. So if you have an IDS in place, it's easy to see IRC traffic, especially if it's not behind SSL, which this was not. So this was just plain text IRC traffic. And this actually used to be really popular for botnets. They would use IRC because the command and control structure was already built into the protocol. So you could have a piece of malware connect to an IRC server, and then you could then issue it commands as if you were chatting to it, basically. So this is an old protocol. People don't use this anymore. Almost every everything nowadays is custom, but for a while this was pretty hot. And it just so happens that this is still active and it's still, you know, blasting out IRC commands all over the internet. So I think it's important to keep that in mind as we go forward. The reason why I chose this piece of malware is because it's a legacy piece of malware. We're not going to be stepping on any toes while we look at it. There's no like ongoing investigations that we'll be exposing or anything like that, so we're pretty safe. And I think it's a great learning opportunity because it has a lot of tricks that are still current today, but they're implemented sort of poorly, so they're actually easier to reverse engineer and get an idea of how to actually handle these techniques without having to look at something that's very complicated, which most malware today is. So I think it's a really good example. But the drawback here is that you'll almost never see malware that's current that uses IRC. So learning that protocol really well probably isn't going to help you too much these days. And learning a lot about the auto propagation through USB drives, most of that stuff is all patched now. So again, it's probably not going to be super current if you're trying to do incident response, but the techniques that we're going to show you today are still very common, and the reverse engineering process that I hope to show you through the tutorials is very relevant to today. So hopefully that makes sense, and with that we'll just sort of jump in here. So I'm not going to do a sandbox run for this, which I normally would do, because I've actually already unpacked it. Thanks, UnPackMe.
UnPackMe.
And we'll be starting with an unpacked sample directly, and I want to show you how you would start in IDA if you just had the binary. You have some idea, like I told you, we know that it propagates via USB, and we know that there's going to be some C2 commands issued via IRC, some connections via IRC, but we don't really have much more information. And so we're going to kind of go into this cold with IDA, and hopefully I can show you some of the initial triage stuff that I would do. Let's open it up here. I put it on the desktop as a sample.bin. Helpful tip if you're reversing and you have Windows, I like to change the extension to .bin because IDA will still pick it up as a binary, but you can't run it because there's no handler for .bin on Windows. All right, so let's load up our IDA here. We'll just choose the default options and let IDA do its thing. Now again, like most videos, I'm going to be using both the Hexraise decompiler and the disassembler. And again, the decompiler is an extra cost if you're purchasing IDA. However, there is a free decompiler in GITHUB, or GITHUB, as I like to call it. I'm not sure why. I think it's just a G-Unit thing. I can just hear 50 Cent saying like, G-Unit. Sorry, I know you guys roast me in the comments for this all the time, but it's just what I call it. Anyway, so there is a decompiler there, which is free, which you can use, and the same process that we show you here will be applicable in GITHUB, but the interface is going to look totally different. Now, with this sample, and with pretty much every sample that we look at from now on doing these deep dives, you will definitely need a decompiler. Just using the disassembler is not going to work, and I'll show you exactly why once we get into this. We're going to be dealing a lot with structures and multiple pointers within structures, and visualizing that in disassembly is almost impossible. You'll see once we get into it. So you are going to need some sort of decompiler of some sort to deal with this. Okay, so we popped in here. Here's our start. So this is the beginning of the program. And what I'm going to do is I'm going to F5 here, open up the disassembly view, and I'll give ourselves some split view. Like I like to see my stuff in a split view. I'll turn this into the text view so we can see it, and I'll synchronize the two of them here. Okay, so now we can see a little bit better about what's going on. I have a better understanding. So we start out here. We can see there's a load library and a bunch of get procedure address calls. And as I've shown you guys in many different videos, I think I'll link the REvil one below. This always means that you're going to be doing dynamic API resolving. So it means that if we look at the imports here, let's go and check out the imports. So there's almost no imports in this malware. So they're probably resolving almost all the API calls dynamically. So that means that we're going to have to do some marking up of those APIs before we can get a good understanding of this binary. And also, if we look here, let's take a look at these. So get procedure name resolves an API based on the string that you pass it. So these are strings. And if you look here, this is a pointer to a string. And if we look at the string, we can see that it's actually encrypted. So we know that we're going to have to do some decryption of the strings Then we're going to have to do some API resolving before we even start looking at what this binary does. So we have 2 tasks ahead of us. And if you guys watched our earlier videos on the REvil string decryption and dynamic API resolving, you'll know that this is pretty standard. And this is something that you're going to have to do on almost every piece of malware you look at. So first 2 things you do, decrypt the strings, resolve the imports. So I'll show you how to do that now, and we'll go through it a little bit quicker than in those other videos because I hope that you have the base knowledge from those. So the first thing we want to do is want to see where they're actually decrypting the strings. And we know that they have to decrypt them before they call get proc address, because obviously here they expect them to be decrypted. So I'm assuming it's going to be in one of these calls here. Let's take a look here. What are they doing? Is that... Looks like they're doing some privilege elevation. So what is that? Nope, so that's actually a string that is not encrypted. So there are some plain text strings in here. All I see is you. All I see is you, buddy.
I'm not your buddy, friend.
All right, so this is actually kind of a funny binary too. You'll see some interesting stuff the developers put in this. So this is not a decryption function. This looks like, I'll just name it, or maybe elevate, right? And they're passing in debug privilege. So let's just take a closer look at what they're doing here. Yeah, so they're looking at the privilege value, and then they're adjusting it so that that's enabled. So they're trying to enable debug privs. Okay, so they're just trying to elevate to get those privileges if they can. And this is, as we can see here in the matching disassembly, this is actually a plain text string. Okay, so since it's not this function, I'm almost certain it's going to be this function. Let's see what they pass into it. They pass you... I love you. Okay, interesting. Okay, so that's a pointer to a string that's in plain text as well called I love you virus. This is not the I love you virus, which is a very famous virus from a long time ago. That is not this virus, but they're passing that in to this function here. So let's see what they're doing with it. Okay, so I see some XOR in here. So this is, again, this is probably our string decryption. And what are they doing? They are looping through, what's v3 here, or v2, sorry. So what is this? Okay, here we go. So this variable here points to the address of this, let's go back here, this pointer right here. And that pointer points to a encrypted string. And if we go back, we can see the next pointer here points to encrypted string. So this looks like our encrypted strings table right here. And it looks like what they're doing is, pop into this here again. Looks like what they're doing is they're passing that into 2 pointers to that string table. So let's name these. Press N for name. Var strtbl0 name var string table 1. Okay, and let's see how they work in here. So they have a pointer to the string table. If the string length of that pointer, so they cast that as a char, and they check if the string length is greater than 0. Okay, so they check that there's actually a string there. And then they have a while loop here, and they say for v3 less than the string length. So they must be iterating through the string here. So what is v3? Is v3 being, yeah. So v3 is a pointer to each character in the string. And for each character in the string, what are they doing? They are, okay, so this was the passed in string, the I love you string. So they're iterating through that string, and for each, okay, that's kind of interesting. So what they're doing here is for each character in the encrypted string, they iterate through the entire string I love you and XOR it with that character in the encrypted string each time. And then once they're done, they invert the bytes in the character. Interesting. Okay, so that is going to look, let's create this in Python here. So we have I love you, which looks to be maybe a key. What is that string here? Let's go back. I love you virus. All right. And then I'll actually just name this malware decrypt string. Okay. All right, so we'll pop in here and then let's say we have some data equals, let's grab the first encrypted string. So that'll be in the string table here. Pop into it. So we'll highlight these bytes, right click, Hex Copy. Shout out to my tool, it's on my gist. I'll link it below. Hex Copy saves you a lot of time, just copies these bytes and copies them into hex encoding. So you can do something like this, .decode hex, and now you have that data string. Now what we're going to do is we're going to do for C in, so char in data. Then we're going to do for K in key, and we're going to do C plus, I don't know if that works in Python. Can you do a plus XOR? Probably not. C equals C, so we'll turn it into a number, so we'll ORD C, and then we will XOR it with an ORD of the key, and we will make this whole thing back into a char so we can save it. Char. Okay, so we iterate through, for each character in the data, we iterate through the whole key and we XOR each time. And then once we're done, C equals inversion of C. And of course that could change us outside of our range for a character, so we'll have to just AND it with 255 to bring us back down into the char space. I want to keep it as a, I want to word this. Word C. Word it, invert it, and then I want to AND it with 255 to turn it back into a character, and then I want to char it back into a character. So basically, when you invert bytes or you do any sort of byte operation in Python, it doesn't really have a concept of that type. So what you do is you basically cast it back into that data type. And of course, 255 is an FF. So this is the same as doing a mask with 0xFF. So you're basically casting it back into the size that it is for that data type. So this is kind of just a hack in Python that you've probably seen me use it many times before. So now that it's back, let's actually create an out string, and we will assign this to the out string plus equals C. Okay. So let's run this and see if it works. And I'll just run it, see if I can make it bigger. Okay. Python, grab this. Doesn't seem right. Feel like I missed something here. So it looks like we did decrypt the string, but for some reason I didn't save it into our out string. Oh, geez. So silly. We wanted to find our out outside of the loop. Kind of a late night here, setting this up for you guys, so walking through it might be a little bit slow. Okay, now let's print out kernel32.dll.
Hell yeah, hell yeah!
All right, sweet. So we've got our decryption algorithm now, which is this. So let's define that. And we want to pass it in data and a key. And we'll make this a whole function, and we will return out. Okay, and if we do something like this, actually, instead of a key, let's just hard code the key, because I think it's always going to be the same. All right, and we'll just pass it data. Okay, and then can we decrypt some other strings? Decrypt, let's grab another string, make sure this works. Let's grab these bytes, copy hex bytes, go over here, paste them in, dot decode as hex, dot decode. Hey, all right, another DLL. Okay, so it looks like we now have a working decryption algorithm for this. And what we want to do now is we want to use the power of IDA to basically decrypt all of these strings which, we would have to do manually otherwise. And I don't want to have to do all this stuff manually. So I'm going to write a little script here. Now, what I think I'm going to do is I notice a pattern here where it's basically all the strings appear to be in one long table, sort of strings table, if you will. And I noticed that there's a bunch of null bytes in between them. So what we want to do is we want to rely on IDA's understanding of this data to basically automatically grab that string for me if I was to pass it in an address. Because of course, if I can pass it in addresses, I don't have to actually copy these bytes out. So for example, I could pass it in this string address here, and I could just have it automatically decrypt until it hits the first set of null bytes. So what I'm going to do is I'm going to use a little bit of IDA scripting to do this. Now, I know that we can use get byte basically. So there is this function called get_byte, and we can pass it an address like this address here, and get bytes with an S. And what is the second argument for it? You want to do the number of bytes, I think. So 1 byte. And then we'll get the byte. So what I can do is I can use that to actually grab all the bytes and just check them until I get a 0. And once I get a 0, then I know that I've got the end of the string. So why don't we knock something out like that here? Let's do like a while loop. Okay, so here's another trick. When you have something like this that doesn't have a defined end, so you're relying on some unsanitized or untrusted data for an end state, what I like to do is instead of using like a while one loop and a break, I like to use a limit count. And this is just to make sure that I don't have a runaway program. So I can do something like this: for limit count in range, and let's give it some high range, like 500. And then I can do my iterations in there. And this just means that if I don't find a null byte within 500 bytes, I'll just end the loop and I won't continue on forever. So this is just another tip. You'll sometimes see these in some of my code if you look at my gist. So for each one of these, let's say there's an EA start _start. And let's use this string as an example here. So we'll just start this out like this. Okay, and then we want to do, we have to get the byte first. So let's call it b equals get bytes, and we'll do the EA. So this is our pointer, our address, equals to EA _ start. Then we want to get bytes from EA. So we want to get 1 byte. And then we want to check if it's 0. So if ord of b equals 0, then we know we have a null byte and we can break. If not, then, okay, we have to have an out string. So let's call that data equals this. And if not, let's go data plus equals the byte. Okay, so we're going to add all the bytes up until we get a null byte. And then we are going to, once we get a null byte, we break. Oh, we have to increase our bytes. So b plus equals 1, right? Yeah, so we increase the byte each time. And so let's give this a shot here, see if this works. Unfortunately, I have to paste this into the little IDA console down here, so you can't see it very well. Maybe I can touch that up in post. Stir and int objects, that doesn't look good. Oh, shoot. I used the wrong counter. Okay, limit count. EA. Plus equals 1. Okay, so let's see if we can make this work 3 times the char. Okay, what's in data? Let's print it out as a hex string. Data.encode code as hex. All right, D7, D3. D7392FF. All right, perfect. So we've basically captured that string automatically now just by passing in this address. So let's turn that into a function called maybe getStringData or something. Okay. All right. So now with the two of these, we can grab our string and decrypt it at the same time. So let's do something like, okay, let's see if this works now. All right, so we can do decrypt string at, let's grab this one right here. I seem to be missing a function here. Let's try this again. I think I forgot to put in the new function after we edited it. Let's paste this in here. Hey, all right, so it decrypts just fine. Okay, cool. So now we can decrypt these strings automatically just by passing in the address of their first character. Now, I want to get big brain on y'all.
You might find that you are big brain as well.
I want to pass it in the beginning of the strings table and probably the, whatever I think the end of it is here. Yeah, it's pretty far down. So the beginning and the end, and I want to basically parse through all these strings. I want to skip the null bytes, and for each one of these strings, I want to decrypt it, and I'll just print it out to the console for right now. So I need a way to basically iterate through all this memory, and for each beginning of a string, basically pass it to that decrypt string function. So let's give this a shot. So let's copy these guys in here. And then let's grab this little function here, see if this works. Oh, Jesus. Okay, so it kind of works a little bit. It looks like we decrypted some strings, but it looks like we're not skipping over the looks like we're not skipping over the strings after we decrypt them. So what went wrong here? Oh, we're in the range here. That is definitely a problem. So let's make this actually a while loop, and we'll say, okay. So the for loop was actually killing our little addition here. So let's give this a shot instead. Hey, all right. So I'll just open that up so you guys can see it. So we printed out all these decrypted strings. Here's all of our functions or our APIs that are going to be resolved dynamically. So we got all those. And it looks like there's some interesting stuff down here too. XOR fully recoded. Virus stealth. All right, stealth USB. Well, we know that it's a USB spreader, so a bunch of other stuff in here. Nick is a command used in IRC, in the IRC protocol. Ping is as well, pong, join. So these are probably the IRC commands. Not sure what this stuff is. Here's the autorun.inf and the desktop.ini. Kind of cool. We can see those strings. What else we have? We have a run key that's being set, and we have a bunch of domains. So these are probably going to be for the C2. So pretty cool. We got all those strings. But the thing is, I want to make the reversing job a lot easier. So I'm going to basically overwrite, I'm going to corrupt the binary, so only in IDA, but I'm going to change these strings so that their bytes are actually the decrypted string bytes. That way we can actually just see the strings directly in IDA. So this is modifying the binary, but only in IDA. It doesn't actually change the binary on disk. And it's just going to make it easier for us to read. And so the way to do this is you'll just do like a put bytes, basically. I also noticed there's something weird here. This is not a printable byte. So I think what I might do is skip over anything that's not printable. So I'll do like a little ASCII check first. And this is actually, this is Stack Overflow thing I have copied. I have these little snippets on deck because I need them all the time. So we'll basically just check if the string is all valid ASCII characters. And if it's all valid ASCII characters, then I'll replace these bytes with the actual decrypted bytes. So let's see if we can get this done here. Okay. So to replace the bytes, we do a patch bytes. So I'm gonna have to write a function, I think. So def. So hopefully this works. I'm gonna copy it into IDA. I don't really have a way to test it because I don't have a decrypted string. Oh, I might have a decrypted string. Let me see. If I go to the beginning of the strings table here, I think the first one is kernel 32. Isn't that what we figured out? So let's see if we can define this as kernel 32. So let's do replace underscore string, and that's the address. And then the string is gonna be what's the very first string in the strings table here, kernel32.dll. Hey, all right, totally worked. So we turned that into a kernel32.dll string. And then since I'm actually going to be decrypting that, and I've already patched the bytes, that's going to be corrupted. But I have this trick here where I'll just sort of check and see whether it's ASCII or not. So what I can do here is I can do if the new string is ASCII, and do new string, then replace the string. And I want to replace the string at EA, right? That's where the string starts. And I want to replace it with the new string. Okay, let's give it a shot. See if this works. Hey, all right, totally worked. So here's all of our decrypted strings. You can see it's decrypted all these strings and it's defined them. So now, yeah, they're basically all strings. And if we were to go into our disassembly here, and we can see that these pointers now point to strings. And they're also recast as long pointers to C strings. So it looks like we have now officially decrypted our table here. Jump to xrefs. So we've completed that, and we're now able to start basically building the dynamic imports so that we can figure out what's going on here. So what I like to do now is I'll find out what these all are, and I'm going to relabel these variables with the procedure address that is being resolved here. And that is going to be very tedious, so I'm going to sort of speed it up. I'll show you how to do the first one here, and then I'll sort of time lapse it for you. Hopefully I can speed this up a little bit. Okay, so we can take a look. This is kind of a nice thing about having the split screen here, is we can take a look here and see what this is. Git proc first. And so then we can press the N key here, rename it. That's basically how you're gonna do this. So you're basically come through, find out what all these different strings are, and relabel the variables based on it. Now you can see that this is already having an effect on the code. It's making it much more readable. So before, this was just a variable that was being used as a function pointer. So for example, if we scroll down, actually we've got a lot of them done already. But if we were to scroll down here a little bit, you might be able to see, like for example here, we have no idea what's going on here. We don't know what that function is. You can see it's being used a lot. You can tell it's a function call because IDA has figured out that it's actually being called. And if you look here in the corresponding disassembly, you can see that it's actually a call to a pointer. And so what we need to do is we need to go back and do this sort of busy work where we define all these variables slowly but surely. Okay, so again, I'm gonna time lapse this. Whew, okay, so we're finally done. That took a long time. So now you can see all of these different resolved imports have all been labeled. We can see there's quite a bit here, and we can also see that if we scroll down here, all of these calls now make sense, right? Since we've done this, this is actually incredibly readable. So we can come through here, we can see they're allocating some memory, they write some memory, and then they have a create remote thread. So we can kind of guess that they're doing some process injection here at the end. And at the beginning, we can see they're basically iterating through some processes. They're looking for, what's this? Explorer.exe. So are they gonna inject into Explorer.exe? Stay tuned to the next video to find out, probably. So this is where I'm gonna leave it for today. So we've basically prepared our binary for analysis. We've decrypted the strings, we've resolved the imports. Now we're ready to start actually looking at the structure of the code and figuring out what this thing does. So I'm gonna save that for the next video. And I'm also going to link the unpacked version of this binary in the description of the video below so you guys can follow along from home. If you have any questions, if I missed any steps or anything like that, just let me know in the comments and I'll be reviewing them. I'm probably gonna make this a little bit more interactive than some of the other videos that we've been doing, because I'm hoping that this can kind of be like a cool sort of sharing tutorial. I know we're all stuck inside these days, and it's, you know, there's probably a lot of spare time, a lot of free cycles. So I'm hoping to sort of, we can take advantage of this and kind of work through this cool binary together. So hopefully you enjoy it. And stay tuned for the next one where we actually look at the structure. Trust me, it gets much more interesting. This is like the boring part that we get over with. It's going to get much cooler in a bit. And like I say, it culminates with a kind of interesting episode at the end. So definitely stay tuned for that. So without further ado, stay safe, everyone. Keep exposing the mechanics behind the malware. Stay curious. Bye.
Well, I got 545 and it's 545. Gotta get a Whopper and a 40 right. Yeah, you know you fucking feel me. Yeah, you know you fucking feel me. Yeah, you know you fucking feel me right.